Today, Tuesday, December 22nd, 2020. We are 48 hours into this eruption, and we have a lot more imagery from the USGS Hawaiian Volcano Observatory. And we're going to go through everything with you guys, give you guys that same kind of analysis, break down all the data, show you guys everything that's going on over there. Let me just pause a second to kind of make sure everyone is joining on, that my streams are set up all right, and we can go from there. Thank you guys for joining. My name is Philip Ong. And all right, I got one confirmation. And I got another confirmation here. So all right, so thank you guys for bearing with me. I'm just starting up. Thanks for joining in here on the evening of Tuesday, December 22nd. We're just past 48 hours of eruption at Kīlauea Volcano. That began 2 days ago, after 2 years of pause of activity on the volcano. So I'm gonna start off by showing you guys this these USGS videos right here. So what you guys are seeing here is a telephoto imagery taken by Matt Patrick in the midnight to 6 a.m. shift last night. You can see the massive amount of lava that's pouring down the crater wall and plunging into that pool at the bottom of the lava lake, at the bottom of the falls, at the kind of the edge of the lava lake, and that's what's feeding the lava lake. This is where most of the volume is coming from. This is the eastern vent, and this is causing the lava lake to rise at a really astonishing level. We'll go through the details of that here shortly. So there you guys go. That's the first USGS video. 2 fissures feed a growing lake at the bottom of the vent. One interesting thing I've noted here, the preliminary calculations suggest that since the start of the eruption, approximately 8 to 10 million cubic meters of lava have been erupted. This is equivalent to over 2 billion gallons, the volume of 3,000 Olympic-sized swimming pools. That's a video by Matt Patrick. Let me show you guys another one. It's taken by Brett Carr, also in the evening. I'm gonna let you guys listen to the sound of this fountain that's caught in this video. Hear the gurgling and the rushing as the gases that are pushing the lava out. And that was that. Here, I play that one again for you guys. So you can see in this video, the lake level is quite a bit higher than in previous videos, right? It's not that far up to this fountain right here. All right, you guys. So those are the 2 videos we got going on here. Right above me, I have the live cameras. This is the latest live image of the thermal image from the USGS webcam, and which one I'll show you guys right here on this plot as well. So there that matches. And above that's the visible image from the Kilauea West cam, KW cam. So I'm going to show you guys. This is the most recent image. Let's reload it, give it a new image here. Most recent image from the thermal camera. What you guys can see is all this orange stuff is the actual hot surface of the lava lake. We have in the middle an island, right? And this island has been measured to be about 50 feet tall, if I recall, by the USGS. And so they say that this is probably, we'll check on this caption a little bit later, but this is probably the first part of the lava that came into the pit that hardened and among the rubble and all the water, and that's been lifted up over the last 48 hours, and it's been circulating as well. So the USGS has this automatic 48-hour animation here. So look at this one first, right? You can clearly see the lake is filling. Notice the highest elevation of the vent, right? The lava lake is coming up very fast, very, very fast. Yeah, currently the USGS says as of 5 p.m. a depth of 470 meters. It's about 470 feet, about 140 meters. So this 48-hour animation is nice, but I want to show you guys the last 48 altogether. So let me switch to that here, and I will show you guys what the last 48 hours look like from start to finish here. You can see that initial very quick venting of the gas. Lava lake piling up very quickly. This is 1 image per hour. And you guys can clearly see the island floating around, moving back and forth. And so let me go to the frame by frame on this one. Okay, so get it lined up here, and all right. And there's our lava lake rising, right? Notice here, let's get a good image. Notice the height of the vent right in here. Yeah. The lake's quite a bit below that. But as we progress, yeah, you guys can see the lake is coming up quite a bit right there. Also interesting is you guys can see this more purplish shades. Those are kind of cooling crusts of lava that are floating on a liquid lava surface. And the thing with these is that they're, once lava lake grows big enough, these things will get hot, will build heat beneath them, which will cause them to crack open, like right in here. And then you'll see lava kind of come and swallow these things, and they kind of sink back into the crust. So if we look closely, we can kind of see places like right in here. Right, we have a big purple area right there, right? Kind of hardened crust. And then right in the middle, we have this crack right in there. If you guys watch that crack in this next frame here, that's what opens up, right? You guys can see the crack has opened up, and we're replacing it with more orange, hotter lava. It's coming from below the crust. You can kind of see it goes back and forth and back and forth. So it's interesting to see how, you know, it's really hot where it comes in, plunging in off of the eastern vent right over here. You can see our island's got a big mass, right? And this thing has got some depth to it also. It kind of be floating up here. But what you can see is that this eastern edge of it, the lava is going to start coming onto it and breaking this part of the plate over here. So this island is starting to get consumed. So let's look at that. You guys can see right there. Yeah. Yeah, so one thing I was pointing out in the update yesterday as well is we actually could see this old piece of crater floor right in here and the lava topping up and over it. So we can look at that aspect, focus on that right there. You guys can see it. I'm going back and forth here. You guys can see it lapping up and on. And the interesting thing we pointed out yesterday is that we have this other vent. Let's get a good image of it right here. We have this other vent right in here, right? This is the lower vent of the western fissure. There's an upper vent kind of up in here along a crater wall that's kind of almost straight down. It's hard to see in this image. But this one right here is going to get swallowed. As a lava lake rises, it's going to bury this thing, and this thing's going to disappear underneath the lake surface. And so there it is. At this point, it's still bubbling. It's still bubbling and hot, and you can see circulation coming from it. Right? But as we progress the animation forward, you guys can see that by here, now it's totally disappeared. So that's very interesting, because if the vent can't put out enough lava, and the actual mass of the weight of lava above it, as the pond rises enough, can essentially balance that out, then that vent may actually stop effusing, and it may actually focus more of the flow out of this finger of the dike, right? The dike being that planar body that has different fingers that come up. That is all one lava blade, and the lava can come up along any of those different pathways to the surface. And so we could shut off one pathway and still be able to come up out the other one. That's what we're talking about over here. So as we come up, we really don't see this lower vent producing anywhere throughout the whole sequence. All right. You guys can see the lake, the actual island itself. The island starts off in the middle, kind of goes straight up, then it kind of goes this way a little bit. Straight up. There it is over to the right. It's as far as about there, and it's going to start moving back this way now. It's interesting to see that. So by this most recent image, you guys can see the island is really the only cold thing left. We have a few spots of broken crust, but mostly you see these cracks in between. All these cracks which indicate the hot lava are coming up, breaking apart the crust, right? So it's really building some thermal mass in there, right? A lot of hot liquid that's kind of getting deeper and deeper, and then that allows it to kind of insulate itself more, and the heat has to escape out the top, and at the top where this crust is forming, and that's why it's going to break the crust to kind of keep doing what it's doing. So that is our play-by-play analysis of the actual thermal imagery right here. Of course, this is not the only image we have. We have all these other webcams, right? So I'll give this a refresh here in the USGS Summit webcam site. Hopefully you guys are all familiar with the updates now that we get all of our data from the USGS primarily, and also social media. We'll get to that a little bit later. But you guys can see here at the USGS Hawaiian Volcano Observatory Kilauea Summit webcams, we have this Kilauea West cam, which is one I have featured right up here. Oh, here's not going all the way up. You can see in the east angle cam, we can see some glow over here. On the right of this image, right, there is a gas cloud coming up. You can see the wide angle camera, that same gas plume, you can see it kind of billowing out more largely when it gets up in the sky. And then further down we have our thermal camera right in there. So our image at almost 10 p.m., very, very similar. Just the island in the middle, lots of red lava all around, and maybe some more crust forming over here. We still don't see this lower vent. Right, I'm not sure if there's an upper vent still pouring in. I think that's quite possible that it is at some kind of weaker pace, but most of the lava has been coming out from this vent right over here. All right, so I will get to questions, but I'm going to try to go through this in sections. So while we're talking about the images and the videos here, I'm showing you guys a couple of the videos and images. We're going to come to the photo and video chronology that USGS has been posting every day. This is also on their webpage. So I'll give it a refresh here. And so you guys can see here this first image, a comparison of two thermal images from the thermal camera 48 hours apart. Right, so the image on the left here, December 20th, 8:20 a.m. The image on the right, December 22nd, 8:20 a.m. In this case, we have 80 °C water. In this case, we have in a range of 500–600 degree lava. Now that's just the temperature it's measuring from this distance, so it's actually, the lava is actually hotter than that. but that's the reading on this actual instrument. And even at the same distance, you can see it's quite a bit hotter for obvious reasons, even though the oranges look the same color in these two images back and forth, right? So this one's actually quite a bit cooler in its water, and this one's quite a bit hotter in its lava. So we'll keep going. This is an image of the field crews, 4:45 a.m., and measuring the lake surface coming up, saying the lake at that point was rising about 1 meter an hour, 3 meters in 3.5 hours. And they have some information there that by now has already been outdated by more recent stuff, more recent measurements of how deep the lake actually is. One thing they do up there, whenever they have a light source, which could be the actual fountain itself, it could be the sun, is they actually shoot this Fourier transfer infrared spectrometer through the gas plume and then try to measure all the different molecules that are blocking that light source and all the different wavelengths, right? And different gases have different wavelengths they actually affect. And so by using an instrument like this, you can then measure gas concentrations coming out. And of course, it's very sensitive. We found out in 2018 presentation research, whether you measure it right here or whether you measure it up here might be a little bit different, right? You kind of need some space away from the fountain a little bit because there's some reactions of the gas still happening as it's billowing up in this first few meters. First 10 meters or so, perhaps, above the actual vent. We can see here quite a lot of gas. This is, a view from north looking south, as they went in their helicopter overflight, just showing the big gas plume coming out of the crater here. So we're reviewing the social media the USGS has put out today. Here's another, this one's a little bit blurry, but view of the vent. Let's move on. All right, so this is an interesting one here. So this is showing that eastern vent and the lava lake surface. One thing that's quite common is in the daytime, only the actual hottest lava will actually look that red, right? And all this stuff over here is all liquid lava as well, but what you're seeing is that really hot crust. And so the infrared camera can see through these plates. They'll be very thin, right? Probably a few inches thick. And underneath that, there's 140 meters of lava. So it might look dark in the daytime and look solid, but it's actually a big liquid pool with a very thin crust on top, like a scum on a soup or on a pudding or something like that. That's hot and comes out and you let it cool in a bowl, something like that. So I want to pause at this image right here just because this is something I've been showing you guys for the last couple of days. Some of the historical photographs. So I'm going to switch back to this 1927 image, right from the Hawaii National Park. And just point out how similar we're looking in our vent with that little lava delta coming down and then the lake surface kind of down over here. Right? Not too different from what we're seeing right here. Right? Same pattern. And so, interestingly, if we look at the next phase of the activity in the 1930s, 1927, 1930, 32 here, see we have a vent that's right at the lake level. And so this might be what we see next. This is maybe getting close to the current situation. By morning, I expect we'll see something like this. And at some point, the lava may actually come up and over top of that vent. And that's been a question we've been getting a lot, is what's going to happen if the lava level rises up to the level of that vent? And so we'll go through that here shortly as well. But first, we'll keep covering the imagery that we have here from the USGS. So one great way to do this is to go over here to the USGS Facebook page. And you can see the activity that all the information they put out here. So, for example, here's a first video I showed you guys at the start of our broadcast. There is that image from the website. Some more recent images are actually up here that haven't made it to the website yet, so I can show you guys some of these. All right, so you can see the northern vent up here. This is the upper vent, the lower vent being buried underneath a lake over right in here. And there's that eastern vent, not that far below, right? So this image is actually pretty good because you actually can see the different levels of the craters in here, different pits. So this innermost pit has an edge like that. And there's another crater with a higher wall that goes something like that. And then there's another one up here. And then there's another one way up here, right? That's the actual caldera wall, that farthest one up. And so you guys can see there's quite a lot of space for that lava to come up. Even if it fills this inner pit, it can widen and fill this other part. And, you know, of course, the broader it gets, the more volume the pit can take. So another image here. You can kind of see, let's zoom into that one. Right, there is that northern vent. You can see much more weakly coming down. The lower pit, that lower vent has been buried under the lake right in there, as we just pointed out. The eastern vent right here is a more vigorous one, and you can kind of see it's dominating the flow. You can even see the crust on here spinning around the island, which looks like this in the actual visible light. All right, so let's move on. Got a lot of things I want to show you guys today. Just a lot of information to kind of gather and compile for you guys. You know, there's a nice view of the island again, right in there. The northern vent, eastern vent. Great USGS photographs. That close up with the eastern vent we showed you guys just a little while ago. So, let's see what else is on the USGS Facebook page here. Same gas cloud. And then here's something I wanted to show you guys. This is an image that they've put out that shows the current extent in red, right over here, of the actual lava surface. Now they've put in blue here, on the inside, the shape of the water lake before it was vaporized in those first half hour to 2 hours a couple nights ago. They've also put on here, on this black dotted line that I'm tracing over right now, the shape of the lava lake from 2008 to 2018. So you guys can get an idea. The lava lake that was here before, about the same size as the water lake that filled in up until a couple days ago. And they're both much smaller than a new pad of lava that's forming here at the bottom, which at the most recent estimate, 52 acres, 21 hectares. The depth of 440 feet, 134 meters as of 5 a.m. this morning. And we've heard that as of 5 p.m., we're up to 470 feet, 140 meters. So maybe the lake level rising slows, just like we saw with the water table, with the water lake, as you know, as the fluid rises in that kind of flared funnel shape, then it actually will slow how high it's rising, because the volume can stay constant and spread out farther and farther and farther and farther in thinner layers. So the actual rate of ascent can slow while the volume coming in stays constant, just because of the shape of that cone that it's in. So for some comparison, here's some imagery that we have from some old USGS publications that we've annotated. Another view of that 2008 to 18 lava lake, and the size in 2016, 180 by 250 meters, or about 600 by 800 feet. Right, if you're wondering what the actual scale is. You know? So if we're talking in terms of 100 yards, 100 meters being about a football field, we're talking about 2 football fields by 3 football fields, 2.5 football fields that way, right? So the water that came in is something that once the initial collapse was visible, something we could predict from the actual well drillings. And I'll show you guys this image right here. And this is something we put together last year. And essentially we have a well on the southwest part of Kilauea called a Keller well that goes down to 160 meters below sea level. And in that well, at a depth of 594 meters above sea level, was the water table. And so we could calculate, based on that level and the actual profile of the collapse pit, which is this red one, the blue being the pre-existing topography before 2018, right? There's an intersect area right in here. Right, there's an intersect area right in there. And that is where the water was building. Essentially coming in from the sides. This is very simplistic, of course, right? But just based on this kind of sketch, we got a potential depth of 50 meters right? And in the end, before vaporized, we don't know if it would have kept filling, how much further it would have actually filled, but the lake level, lake depth got to exactly 50 meters before it vaporized away. And its potential width, 260 meters, or 2.5 football fields again, right? Which is about the same size as the Halemaʻumaʻu lava lake from 2008 to 18. And as we saw in this previous image, over here, right, these are about the same size. These things offset 90 degrees, right? So that's interesting there. And so from that projection of the intersection, we kind of just very roughly sketched out a little oval of what that might actually look like, right? Okay, without going too deep into the topography, the lake would fill that bottom part of the pit next to this down-drop block, right? That has not been buried by lava, giving us an idea of the level. And so I'm kind of stepping through this just so you guys understand like the process that we go through here. And in the end, we make estimates, we make essentially some kind of predictions of what might actually happen, and there is some error involved, but a lot of times it does work out. So here is the actual water lake in gray, right? And superimposed on it was our projection that we put out back in August 2019. So some more comparisons. Did want to point out, let's see where I have it here. Maybe this one, right? For those who want to compare this to the size of Green Lake, which was buried by 2018 eruption down in Lower Puna. To scale, it was this size. It was 135 by 80 meters, right? So about 1 by 1 football field, right? 1.3 by 0.8 football fields. Football lengths, field lengths. And so in comparison, everything we've had going on now really just dwarfs that. All right, so fascinating image by USGS there. This was the second one I put out today. In fact, there's an older one I want to scroll down to you guys to show you guys. So USGS also reports on California volcanoes. Here's another of the movies that I showed you guys. This is an INSAR, which we'll cover here a little bit later, showing deformation on a volcano taken from satellites. We'll dive into that a little later with time to explain. And here's an image this morning of the USGS deploying a GPS receiver by helicopter, landing down within that lower block, right? Volcano Observatory is up here, up on this over cliff. So you guys can see the eruption plume right over here. This is that second ledge up that I pointed out from another reverse angle before. So it's fairly safe right over here. And you're installing a GPS station because you really want to see if the magma is pushing the ground up, how far over that spreads, how localized it actually is. And that kind of relates to the satellite data that we'll look at as well. Okay, so just a little bit further back on here, there's 2 images as well. This video I showed you guys yesterday of the actual time lapse from Mauna Kea, from Gemini Observatory, showing the eruption with some lightning in the clouds. Worth pointing that out again. Lightning in the clouds right in there. But this morning, the measurements, and here's the one I want to kind of end on at the USGS Facebook. This image was put up last night, but this one is actually superimposing thermal imagery right here on the satellite surface. So you guys can really see here the island right in the middle. Right, there's a big piece of crust still when this image was taken. But you guys can see the vent right in here, eastern vent, northern vent, and the filling pond of lava right in there. You can see that first inner crater, the edge of it, which is right around here. You can see that second crater, the edge of which is right around there. You can see that third crater, edge of which is around there. And the fourth one is the one that goes off. You can see another piece of it way over here. And back over here. That. So that is fascinating. By that point in time last night, this was reported as a 22-acre lava lake, which has grown since then. I'm sorry, 33-acre lava lake, 13 hectares, which has now grown to the 52 acres by today. So lots to see there in the USGS page. And let's move on now to show you guys our most recent update. So there's a lot of pretty images, but of course there's a lot of information here as well. I mentioned a little bit earlier that they put out a little bit of data alongside the updates on the images and the videos. But they've also now switched to since we're at alert level watch, we now are going to receive daily updates from the USGS on Kilauea Volcano. So this update is from nearly 12 hours ago, 10 hours ago. 11 a.m. almost noon, right? And so at that point in time, they say the current depth was, which I've kind of mentioned a couple times already, it's currently to 470 feet. At this point, it was 440 this morning. They say summit tilt meters record slowing deflationary tilt. SO2 emissions remain high, estimated around 30,000 tons a day. So that's a new number we haven't seen before. 30,000 tons per day. Is the amount of SO2 being produced by this eruption. We knew it was massive based on the all gas data we covered yesterday, and we'll cover that again today a little later on. But that's a noteworthy number, 30,000 tons per day. For reference, some kind of the industrial regulations that EPA puts on factories are down like in a 10, some more like 30 tons a day, something like that. So we're well over that. Of course, there's no regulating a volcano, but compared to any kind of human emissions, this single event is kind of what drives it. Now, not to get into a discussion about climate change and all of that, but volcanoes do have some effect, perhaps smaller than the combined mass of all humanity, but in this particular volcano, compared to one factory, this is putting out a lot more. Seismicity is elevated but stable during the last day, with few earthquakes and tremor fluctuations related to the vigor of fissure and fountaining. So last night, the lake was 487 meters, 1,600 feet below the crater rim. So that thing is still rising, but it's still way, way down there, 1,600 feet below the crater rim, and rising at more than 1 meter per hour. And that was the report this morning. And it seems like it's slowed, right? Because it's rising into a widening space. So, right, farthest deep vents remain the most vigorous. The middle vent pauses activity between 7:30 and 8 a.m. Hawaiian Standard Time. All right, so that's another piece of information that we have. And here's another good one. As of early this morning, preliminary calculation of volume suggests that since the start of the eruption, approximately 10 million cubic meters of lava have been erupted. Surface area of 33 acres. All right, so that's most of the meat of this update here, but we can do more with this. It turns out that if we know 10 million cubic meters and we know how long it's been, we can now come up with essentially what we call like a bulk effusion rate, like the rate of how fast the lava is coming out. We can compare that to other eruptions we've had in the past too, and that's a question we've seen as well, is how does this relate to past eruptions of Kilauea? What about fissure rate? So the calculation goes 10 million cubic meters over the past, let me look at my notes here. Depending if you use the range of 31 hours would have been this morning. If you use it all the way to now, 48 hours, and still use it 10 million cubic meters, you can kind of then calculate that works out to, we're going to put this in units of cubic meters per second, right? So imagine like 1 cubic yard cube meter per second. That's the unit we're measuring in. So by those calculations, the lava is coming out of the ground here at the zone of Kilauea, somewhere between 60 cubic meters per second and 90 cubic meters per second. 60 to 90. 60 to 90 cubic meters per second. Pardon my shoddy mouse drawing here, but just to kind of make it obvious for you guys there. So how does that compare to fissure rate, right? 60 to 90 cubic meters per second. So I'm going to bring up here this plot from a paper in a science magazine that was put out last year by the USGS, and we're going to look at, this is actually a paper that deals with the pulses, right? So times when there were pulses in a channel at fissure rate, levels down, levels up, and so you actually have variations in the amount of lava that's coming out over time, well, which is interesting, as well. So we can kind of see the range of it. And zooming in down over here, we can see on this plot bulk rate cubic meters per second right there. That's the same unit I'm putting it in, right? So by this comparison, what Kilauea Summit's producing now, 60 to 90 falls down in here, right? We're below even the lowest points, the drops, the valleys, the lowest points of Fissure 8 erupting. Now, when Fissure 8 was actually at its peak during those surges, it was somewhere in the order of 20 times greater rate than what we're seeing at Halemaʻumaʻu now, right? During its low points, maybe only 3 times more than Halemaʻumaʻu. But the range for Fissure 8, 3 times to 20 times 20 times larger volume coming out. Okay, so Fissure 8 was really like a record-breaking deal, so maybe we don't want to consider the actual record-setting eruption. And what about other eruptions on Kilauea? So we'll look at that as well. Just another plot here from that kind of same paper, showing a range from bulk effusion rate down here, from the range of 300 to around 1800, somewhere like that. Okay. All right. And I wanted to point out here as well. So they actually see long-term surges plotted in these two images down here, but there also were shorter pulses, right? Kind of gas-driven bubbling. And those, even though they're much shorter lived, did reach levels of 3,500 cubic meters per second, right? But pretty rarely, only a few points down in there. Mostly you see a big cluster around 1,000 cubic meters a second, and another one maybe around 2,500, 2,000 to 2,500 cubic meters per second. Similar over here in infrasound. So we're well below that here on Kilauea's summit today, right? Well below that. But what about other places in the world? This is an old paper. I'll show you guys. It's back from 1981 by, not sure how you pronounce this gentleman's name, Waj. Variations of magma discharge during basaltic eruptions like we have here. And he points out that in 1970, Hekla volcano in Iceland actually got up to 7,500 cubic meters per second for a very short time, for the very first few hours, and then dropped off significantly to rates more around 200, 100, more what we're seeing now. So not that unusual for the later terms, and who knows about this early phase, how much lava was actually coming out. It might have been quite a bit higher as well. It's actually quite common to see this pattern of, you see lava fusion going up, and then down, and tailing off until something else changes or ends the eruption, somewhere over here. Right? Looking at another eruption, 1961 in Iceland, 600 cubic meters per second. Okay? Mauna Loa. So I'll read you guys this table. Like, what matters is this column right over here, cubic meters per second, and we see the range of 20, 38, 53. So the lowest I see is this one, 2.5, right? 1855, 1856. The highest we see in 1975, 332. So 332, not quite as high as Fissure 8, but still very, very massive flow. Of course, you see Mauna Loa has a big range, 200, and there's a 7, and there's a 50, and there's a 6. And so our estimate of 60 to 90 for what's going on at Kilauea now, actually you see quite a bit of activity falls in that kind of pattern like that, right? In a 40 to 100 range. So not that unusual. We're not anywhere at the higher range. We're kind of in the middle range. Definitely not at the low end either, right? Not at the high end, but we're in the middle compared to what Mauna Loa does. So what about Kilauea? Kilauea, we also have these calculations. So once again, meters per second, and we have an 81 back in 1840, right? That's pretty similar, range of 60 to 90. So we know that that can happen. That was a lower East Rift eruption, actually, the last one before 2018. That was of that size and flux, like this kind of range, right? Although we really dwarfed that in 2018. But normally, Kilauea has more in a range than what you see here. 2, 0.2, 1.8, 10, right? These are all between 1 and 10. There's a couple of 20 to 30 range. And here's one, 1963, we had a 68. So that's in our range what we're seeing today as well. 1971, we had a 246, right? So, and similarly, in 74, some of those fissures, 216, 432. So we've had pretty big eruptions right there of Kilauea as well. And we're in a kind of middle range as well. Kilauea kind of, we now know that fissure rate was at the very, very high end. And this is the, kind of the normal high end, normal low end. And then here we are in the middle today, right? This paper, since it was 1981, predates Pu'u'u eruption. And so for Pu'u'u, we actually have done measurements as well from satellites and other things like that. And it comes out to between 2 and 4 cubic meters a second, right? So that's, what is that? 10 times less. 10, 20 times less than we're seeing at Halemaʻumaʻu today. Okay, so I don't want to show you guys too many tables, but there's an interesting plot here, 2 interesting plots. Mauna Loa and Kilauea. And what they're doing here in this plot is they are putting duration on one axis and the effusion rate on the other. And what they see is a pattern where if you have a very high effusion rate, you are much more likely to have a short eruption. And if you have a low effusion rate, you're much more likely to have a long eruption. And so if we're looking at our range of effusion, and this is Mauna Loa, of course, we'll look at Kilauea next, but if we're in a range of 10 to 100, somewhere in there, normally on Mauna Loa, that would lead to an eruption that's in the order of 10, 20 to 30 to 40 days. All right, let's look at Kilauea. We're really interested in. So it doesn't quite plot as tightly. You have a much bigger cloud here, right? Than we had at the other one. But still the pattern holds, right? You can see that if we're up in the thousands, normally less than a day eruption, although I've just showed you guys that in 2018 we were higher than that. We would have been an order of 100 days, 2018, and 1500. So we would have been plotting somewhere right in here, right? Would have been way, way above the mark. And of course, we can talk about the reasons for that some other time. But the dynamics of Caldera collapse certainly had a lot to do with that. So normally, Caldera is not going to collapse now. It's already collapsed. We have an effusion rate between 100 and 10. We could even go and say, okay, 90 to 60 is somewhere actually right in there. And we can see the range, right? The range of eruptions on Kilauea has gone from less than a day to tens of days, 10, 20, 30 days, right? So that is another line of reasoning and basis for best guess prediction of how long eruption will actually last in the order of a couple weeks, right? Which we've been mentioning for a couple of days. Of course, no guarantee. There's lots of times that lava's been filling in collapse pits where we can't see the rate. We'll have to follow up on that maybe tomorrow and show you guys some of the sequences of collapses and refilling and how that goes over time. But I think this is super interesting, right? To see how the flux meters per second relates to the duration in days of activity in historic eruptions of Kilauea. All right, so let's move on, and we're going to go and look at the summit topography as well. But one thing that maybe is on everyone's mind is if that lake rises up, right? And so we are now at, I'm going to change my color of my pen here. Let's make it red. You guys can't read these numbers on here, I'm pretty sure. I'll say zoom it way in, right? But these are in meters. This is a topo map that I compiled from a DEM release by the USGS So 520 meters is the depth of that lowest part of the pit. You can kind of see over here, this is that collapsed crater 4 block. It's a little bit less steep right in there. But we now know that the pit has been filled. The lake is about 140 meters deep. So if we started at 520 plus 140, that gives us 660. So our 660 line is this one. So the lava lake is probably following that contour right there. Right? That's the size it is right now. So you guys can see if it were to rise, let's say it rises another, I don't know, 150 meters, right, to 710. 710 would be all the way here, all the way around. I'd be losing a little bit, but something like that, right? Still easily within a collapse pit, right? In fact, I can zoom out a little bit more. Zoom out a little bit more here. And let's see, how high can we go? This crater edge right over here, we're looking at about 800. This is about 800 meters elevation here. So the 800 contour line might go actually in here a little bit. And then around like this. So if it gets up to another, if it doubles its depth again, right, then it may spill out first onto this piece of this upper ledge right in here. Now it'd have to go on for a long time at a higher rate, and I just talked about how the rates seem to go down over time, how we have a lot more space to fill, so it seems highly, highly unlikely it's going to get up this high, right? But you guys have been asking, like, what happens? How far can it actually go, right? So that would be the 800 meter elevation, right? Let's say it actually gets up to, what's our next level right up here? 900. So 900 contour goes something like this. And we actually start spilling over here. 900 goes something like this. Like that. There's a 900. Try a little more quickly. And so still within the pit. That's if it fills up all that way. And what if it goes to 1,000? Okay, let's zoom out a little bit more. 1,000 now is all the way over here. Yeah, 1,000 goes around this way. All to there. All right. What if it would take for it to actually get up to this part of the crater floor? Well, this is at about 1070, 1080, all through here. So if we can get to 1100, then we will be all the way to this level over here. Right, now it would have to be massive, massive, massive. Now this might be what the pattern we actually see over the next many years, as it fills in over and over and over again. And we'll talk about that tomorrow when we go over all the collapse sequences, the historical record that we do have of Kilauea as it's collapsed and refilled and collapsed and refilled more times than I can mention. So, but that's kind of a little bit of an insight into the topography of the area. And so the next question you might have is, well, if it does come up, well, we know it's not going to come up all that way, all at one go. What if it comes up another 20 meters and buries the actual vent it's coming out of? What then? Well, then we might have a situation more like Kilauea Iki. And so I'm going to take a minute here to step to the story of Kilauea Iki, which is now 60 years old, 61 years old. But I think it's worth revisiting at this point in time, just because there are a lot of analogs to understand what happens when a lava lake actually rises to the point where it drowns a vent that it's coming from. So Kilauea Iki, Began with a series of fountains, a fissure on a wall of a crater as well. This was way, way, way above the crater floor. So I'll show you guys this animation of the fissures fountaining in 1959. And here's a view of that fissure on a crater wall, halfway up the crater wall of Kilauea Iki. Some segments of fissures all through here. You can see they poured down a crater wall, filled in up the crater floor, big lava flows. There's actually another crater up here, but there's a cliff, so a big lava falls that kind of went into it. And what often happens with these eruptions is that as the lava drains down into the hole that it's come from, once it's let out its gas, it kind of heals and plugs the crack in many, many places. So the idea basically is that gas is what's driving many of these eruptions. When magma is deep down underground, the gas can be dissolved in the lava. Once it comes up above a kilometer underground, about a half mile down, those gas bubbles start to form. And once bubbles start to form, they start to expand and to rise. And once they expand and rise some more, they're basically going to come up and up and up and grow and grow and grow and grow all the way to the surface. And they got to escape somehow. Or those kind of collect until they build enough pressure to actually bust open a new vent, right? As we essentially saw. So as that gas is rising up, it's essentially burping out, right? It's not unlike a bottle of champagne or a can of soda, can of pop, whatever you guys call it. If you have a bottle of champagne, you shake it, and you crack that cork, the whole thing is going to erupt. You can't just barely open a bottle of champagne like that, right? You know, once you pop the cork, the whole thing is going to all the gas is going to come shooting out at once. Once the gas comes out and the champagne is thrown into the air because of the gas, the champagne, which is now flat, falls back down to the ground. And the champagne left in a bottle also ends up a little bit more flat, right? So the lava that's falling back down to the ground is also a little bit flat. It has less gas. It's a little bit more dense. And that means that when it flows into that crack, it's going to want to sink down, and it may actually be able to close off the smaller cracks, especially if we have one of these blades that has fingers, right? And we can just block one finger. Okay, well, that one come out of here. We'll block that one. Well, it's come out of here, and so on and so forth. It can kind of just redirect the output to the place where that crack is the widest, right? And in this particular photograph, that's going to happen where this white arrow is located. So you can't really tell visually from this fissure right now that this right here is the actual widest spot of it, but this is going to be where we now have a giant cinder cone over top of this vent. And I'll show you guys how that progresses. So the story of Kilauea Iki continuing here. That one single vent, the next day, here it is. All right, it doesn't look too unlike what we see today out of the actual Halemaʻumaʻu 2020 event, right? There's that vent up there. You can kind of see it's making this lava rapids, filling in a crater, right? And there it is, fountaining higher and higher. These fountains were actually very, very high. So this Kilauea Iki eruption is different from Halemaʻumaʻu in that way, where we had a lot more pressure. Magma was coming from much deeper, and so it shot into the air much, much higher. And so that part of it doesn't really relate, but we can kind of see what it did in this situation, right? You can kind of see that our lava falls has now become lava rapids right here, right? We're almost level, almost filled on this crater all the way. Excuse me. Okay, to show how high this fountains actually were, this is a view from Jagger Overlook. So you can see the caldera walls and see how high above this fountain actually went, and this is a cinder cone forming on the downwind side. So that part is different. However, you can kind of see what the fountains look like as they were growing and kind of feeding rapids going into the lake in this early part of the eruption here. Excuse me. All right, so you can see a big jet of lava. You can see it's all kind of splashing down, and it's kind of splashing to more and more lava pond here at the base. I gotta change my color again because now you can't see the red on the red, right? So kind of splashing and forming a big pool at the base here as it falls out, where all this lava falls out. right? So ours is kind of gushing more just like this, and not having quite as high an arc, not quite as much gas stored in there. It's kind of just more bubbling, gushing out this way, right? In 2020. But you guys can see what happened next is the lava lake that was fed got to the same height as this vent right in here, right? So that did change the eruption, right? It didn't stop the eruption. It changed how it actually happened. It did stop it temporarily from time to time, and I'll show you guys how that actually happened here. So the fountain had come up through the lake. So here you guys can see the fountain coming up through the surface of the lake, splashing onto that crust that's forming, but the crust is still cracking and hot underneath. You guys can see all the way over here. You can also see how the fountains change their heights very quickly. We actually had periods of the fountains shutting off entirely, and then rising back up, then shutting off entirely, then rising back up. Right? As the fountains went through that lake of lava, they actually formed waves. In Kilauea Iki, we had actually waves moving across that surface of lava from the actual sheer power of the jet moving through it, but also the fallout, right? From these lava waves over here. You guys can see that moving across. So that's an interesting video of Kīlauea Iki. Fascinating aspect of what can happen when you have the fountains going through the lake. So here is a plot of the actual volume and essentially the depth of lava in Kilauea Iki. So the eruption had 17 different fountains. These fountains are depicted as these bars up here, right? We have a date on the bottom, November to December of 59. So the first phase, before the vent was drowned, is this big box over here, right? So the lava can just fill in, fill in, fill in, fill in, fill in. When it got to the same height as the vent that it was in, it would fountain up, but then it would drain back down into the vent, because essentially the mass, the weight of the lava in the lake, would equilibrate to the force of the gas pushing out of the vent, and then start draining back into it. It would overcome it. So essentially, the lava would push harder, then essentially allow the gas underground to recharge and build up enough pressure, so it eventually would overcome and it would push lava back out again and start fountaining through the lava. Then eventually, as the gas pressure wound down, it would kind of get smaller, and then the lava would come back in and drain back into it. So you can see that all these different peaks right in here, up and down and up and down. And actually, we built a little levee, like the actual vent got taller. So that allowed the lake to get a little bit deeper as well. And so when that happened, the lava depth went up right in here, right? So here's the depth of the lava we had within that crater. It's a big, massive crater, Kīlauea Iki. And you can see that the lava level is there, reached in the end a depth of 126 meters, 413 feet. Right? So, we are already past that in Halemaʻumaʻu. That's noteworthy, right? Halemaʻumaʻu is a steeper, it's a smaller diameter, so it has less lava in it altogether. We actually know that so far about a quarter amount of lava that Kilauea Iki put out is what Halemaʻumaʻu's put out. So Kilauea Iki was 4 times larger so far as volume, but because it's in a smaller pit in Halemaʻumaʻu is already got a much deeper lake. So you can see that that's an interesting aspect. Those of you guys who are from Hawaii or have been to Hawaii, been to National Park, been to Kilauea Iki, one of the most popular hiking tours in the National Park, you can see that we've already passed the depth of Kilauea Iki on there. Okay, we'll move on. During the fountaining events, you'd see these kind of shock waves moving through the fountain, right? Kind of, if you've ever seen a fire hose going, you can kind of see like pressure waves moving through the fluid as the fluid is jetting out. That kind of effect when you have so much gas and such gigantic fountains, which is not what we have at Halemaʻumaʻu today, but what happened at Kilauea Iki, and then a drain back that occurred sometimes within a few minutes of a view like this, where lava is going back into the vent, right? You can see lava is still draining back from the upper parts of the cinder cone. How quickly this thing shuts off. It's still red and flowing. So let's show you guys what that might actually look like. This is a video taken of drain back inside Kilauea Iki in 59. Right, so the same vent that was just putting out the lava, you can see that the lava is just pouring right back into it now. All right. At the same time, you'd see parts of the cone collapsing, falling down. Right, and so now you can see the lava lake's got this crust. It's getting harder and harder, and the draining is happening more in here. And so that's what allows a landscape like in Kilauea Iki. We had this very deep crater. Here's our original vent. Right, lava rapids cascade down in here. Yep. Went from this view to this view after the eruption. And today, a more recent picture taken in 2018, showing more of the collapse pit at Halemaʻumaʻu in the background now. Here's Kilauea Iki with its cinder cone puʻupuʻai and its frozen lava lake and the hiking trail going across it right through here. Yeah. One last thing on Kilauea Iki. We do know that in the end we had 38 million cubic meters of magma is what filled that crater. There was essentially an up and down and a lot of magma drained back, but without going to those details, the actual amount of lava in Kilauea Iki floor, 38 million cubic meters, we have about 10. So we're at about a quarter of that amount so far of what filled Kilauea Iki. So that's of interest to some of you guys. And with that, I will move on to the gas. And I will take questions here at the end, but I'm going to keep the program moving here and show you guys this DOH, Department of Health, Hawaii site, which for the island is showing green at all the sites. Now this particular map seems to show green at most of the places, so I like to also check the national park monitors, and so we'll scroll down here. You can see over at Kahuku that this morning there was some bad SO2, bad particulates, but that perhaps the wind has changed and it's been fairly clear this afternoon. There and there, right? So we'll visit the VOG map page once again, and we can see now by their colors that they have updated their SO2 emission volume, right, based on the measurements that HVO has taken. And so now they can actually simulate much more precisely the concentration of particulates and SO2 that is emitting from the volcano. So essentially the SO2 is the pure form of the gas, but as it flies through the air and reacts with the water vapor and has sunlight, it can then become more of these sulfate particulates that actually are small particles drifting through the air that are obscuring view. That's what we call the VOG. And so people who are on the Kona side of the Hawaii island right now and are seeing the sunsets starting to be obscured again like they used to be back during the lava lake days, and much of the eruption era of Kilauea are now seeing that again, right? Their sunsets are getting blocked by all the small particles that are caused by reactions of the gas in the air. So you can kind of see this one animation here is going to kind of zoom in on the island. You can see that certainly from our point source here, I'm going to change my color again. From our point source over here at the summit, we have the worst areas around a national park, Pahala, Ocean View, right in there. Okay, let's back up here. And these guys, if you scroll down, also put out whole island simulation. So at a bit wider view, you can see here this plume kind of trailing off across the Pacific, right? Heaviest red areas right here in the southern part of the Big Island. Okay, so let's look at windy again. Let's give it a refresh. This is the windy SO2 layer, windy.com. So you guys can see our plume getting dragged across the Pacific. There's some kind of back eddy flow pulling stuff this way as well, right? But I'll zoom out a bit here. You guys can see this is a big global phenomenon, big sulfur cloud around Hawaii Island in the middle of the Pacific Ocean. All right, so keep going on the gas here. And one thing we've been doing is checking USGS Twitter. I'll give that one a refresh as well. USGS has been doing a fantastic job on their Twitter and Facebook accounts to remind us, give us updates, right? So here we have our measurement 470 feet deep at 5 p.m. That's where that is coming from as of 7:48 p.m. There's a video we saw earlier, or the same images, and another example of some gas information here from Simon Karn. Update SO2 emissions. Strong plume wrapping around the south side of the Big Island. So this is the actual satellite observation as opposed to the model we just saw before. So you guys can see it lines up fairly well. There is a lot more red you guys can see right in the Kona, South Kona side right over there than you'd expect. So it's more of the USGS Twitter feed right in there. So including more updates by the national park on how to visit safely. We covered that a little bit yesterday as well. A nice image I have reposted there as well. So let's switch over to Simon Karn. Let's reload his. You can see, once again, the initial eruption onset. There is SO2 plume measured on satellite we just saw. Here you can see the GOES satellite, right? So this is very interesting. Very clearly have wind direction coming from the east. You can kind of see we have a split of flow that goes around the island, right? Some stuff kind of comes up and across as well. Up and across that way. Around that way, right? So our plume right in here is getting dragged over this direction, right? But you can see, unfortunately for Kona, all this gas is getting caught in this little eddy right in here, swirling around. You can imagine if you're in Kona, looking west at the sunset, you're looking right into this mess. Right? All right, keep moving on. I know I've been going for a while, guys. Here is the statewide monitor. Let's see what it shows. And so this one looks a little more accurate. Now we're seeing some moderate air quality levels in Kona, right? Kailua Kona, Captain Cook, Ocean View are all showing yellow. Yeah. So just to emphasize, this is our main impact to people living on the island today. Is going to be this gas output, particulates in the air. I believe, I don't know if I showed you guys the image from the USGS of their solar panels. Where did it go? Back over here. And back over here. On the USGS page, here we have captioned of tephra on a solar panel of the station. This photo shows a solar panel with about ½ an inch of volcanic glass that accumulated in the perhaps 20 hours previous, 18 hours previous. So this is very close, of course, to the pit right in there, but this is what's happening downwind in lesser concentrations down in the Ocean View and Pahala and areas of Kau as well. So, okay. I do see there's still questions coming in. Keep them coming, you guys. I will kind of scroll through them all here at the end. But let's, for now, go back and revisit our aviation. Right, so we reported yesterday that there was the FAA had placed a flight restriction up to 34,000 feet following the USGS red aviation warning. Of course, USGS dropped their aviation warning down to an orange. And what we've seen today, this morning, is that the FAA has also kind of revised their flight restrictions. So now the restriction is up to 9,000 feet, not 34,000 feet above sea level, right? But the radius, 3 nautical miles. rather than 5. Right? So it's getting a little better for air tours, air touring, that kind of thing. Right, so a few more things, you guys, before we get to the questions. Let's cover the deformation. Let's give this USGS a reload. Kilauea deformation data. So our 2-day plot's just showing shallowing curve, so slowing deformation rate. If you look for the past week, you see the same thing. You don't see much other evidence of anything else there. We can look at the scale as well, but let's go back to the past month, as I like to do, and focus on this one a little more. So our scale up here, this very top part of this curve, is at around 10 microradians. The bottom part of this curve is somewhere around -20. Now, microradian is a unit most people are not familiar with. If you guys are joining our broadcast for the first time, you may be familiar with degrees of tilt, right? If you remember geometry, degrees can be expressed as radians also. Microradians is a very small fraction of a radian. An equivalent analog is having a penny under a half-mile long bar of metal. So a half-mile long bar inclined the width of a penny is about a microradian, more or less. So we're measuring very, very small amounts of tilt, although when it gets to this scale of 10, 20, and you might even see more than that, then you do start seeing deformation on the surface. You can actually see cracks forming and things like that. So interestingly, but we've been talking about this, how December 2nd was the first intrusion, the lava injected underground and reached the surface. So we had a big excursion going upwards, right, to about a little less than 10, from a little less than 12, so that might have been, well, let's call it 20 microradians in there. And from here, plus 10 to -20, we've now dropped down 30 microradians. So we've come down farther so far, and we're going to keep going as well, right, until this eruption is over. If we look at GPS signals, we're starting to see the first plots, first signals here coming in a little bit lower, right? So this is basically showing a trend. This thing's going to drop and perhaps deflate at some rate. Whether it deflates more like that or more like that, I'm not quite sure. Somewhere in there. But you might think something like that will happen until the eruption is over, and then it might resume a flat and eventually back up again, right? So that's what we're waiting to see, is how that will actually look. So that's our GPS. You guys can see how it's a longer term trend, and no change at Pu'uo'o still, as we've been repeating. It's worth mentioning again. Okay, so let's go to the INSAR. INSAR is essentially a way that the satellite flies over the ground. It scans it with its radar. It flies over a second time, scans it again. You can then take the data sets and you can then subtract them and see the differences in elevation. Of course, there's a lot of complicating factors: the atmosphere, the angle that you're looking, the shape of the ground where it is, vegetation, all those things affect it, right? But kind of moving past all those caveats for now, what this is showing is a range change of, from blue to green, we call one cycle of 1.5 centimeters, right? So blue to green across the purples, right? So that would be something like this blue to this blue to this blue. So we might have something like that, like 2 different cycles within here. What you see is this kind of pattern right in here to the untrained eye. This is an area where the ground is dropping, subsiding. It's like it's emptying out. This is the source of the eruption is under here somewhere, right? And it's feeding out over here. It fed this other intrusion, December 2nd, over here. And so no surprise that this is an area that's sagging. The ground is sagging down as that extra pressure is relieved, right? Now it's harder to see as well, but let me zoom into it. Maybe you see a little better. We have 3 bands right in here too. 1, 2, 3. So it's hard to see this really speckled ground because it's really steep cliffs in here, and the angle of the satellite coming to look at things really, really not getting the resolution, right? But it looks like you have some inflation source right over here. Right? Not surprising, this is where the vent is. So the magma is going from here to here, coming out of the ground here. This is swelling, and this is sagging. That's what the satellite data is actually showing us. Right? You can kind of see this area of subsidence. Something like that. Right? Okay, so if we look at the intrusion map put up by the USGS, you can see that right under here is where they modeled that dike had to be, at least in that area. So the source is right in here, and deflation is happening all through here. Then you could even have some of the lava that went into this dike could possibly be flowing back and going into here. That might happen later on, it may not happen at all. It kind of all depends on the shape and dynamics of what's happening under here. But essentially we have our source is common right underneath here. All right, so this plot's showing a lot of earthquakes. Let's just check in on the earthquakes, but before I do that, I want to show you guys this kind of model from a science paper, right? So this is 6th of May 2018, before the lava lake drained all the way away. The last time we saw lava in Halemaʻumaʻu, in fact. And lava was dropping down at 53 meters per day. That crater was inside of another crater. That's Halemaʻumaʻu crater that was inside the caldera itself. During the collapse, 12th of June, the lava lake disappeared down over there. The crater kind of expanded. It's growing over here, and the outer edges are kind of, we're starting to have more of that stepwise collapse, like all those different levels of collapse that we showed you guys over the course of the broadcast. And of course, they're modeling this as being a magma storage area right underneath there. And no surprise, our dike rectangle is right over here. Our new vent for the eruption 2018 is here. And it's pouring in and filling in this lower section of the lake. All right. A few last things. Check on the earthquakes. These are the earthquakes for the whole island. You guys will notice that most everything else has gone quiet. We had an earthquake in Mauna Kea just recently, but Mauna Loa is very quiet. It's basically waiting for Kilauea to do its thing, it appears, right? All the earthquakes in Mauna Loa, everything is basically stopped. Kilauea is the one driving the bus right now. This is an aftershock, it seems like, to a very deep depth. To an earthquake we had last week, it was a 4.4 in the same area, very deep underneath Mauna Kea, settling at the crust. We still have our Pahala earthquakes, although a lot less of them. We did have one more recently over here. It was a 2.3, also very deep, 30 kilometers down, 20 miles down. And you can see that hardly anything in the south flank anymore. Hardly anything in the east rift. Hardly anything in the summit even, to be honest. Right, in the last 24 hours, hardly any seismicity. And the reason being that the magma has already found its path outwards. There's no need to crack any more rock. It already has an open nozzle, it just flows out of the ground, and everything else is now sagging and depressurizing, and that's going to cause it to quake and crack less. Yeah, if that makes sense. So, time for questions. I'm going to start off with a couple questions that I picked from the USGS site that are something you guys might ask as well. And then I'll scan the feeds here on YouTube and on Facebook and see what you guys are saying. So, question from Wyatt Everhart to the USGS. I wonder if we will once again have a long-lasting lava lake. And they reply, yes, very interesting thought. The previous lava lake was 12 acres in size. Interesting statistic, right? Ours today, up to 52, was active before it drained away. This morning when they answered, this was 33. Now we're up to 52 acres in size. It's fed. And here's our answer. It's unclear how long this eruption will continue. If fissures stop feeding lava to the lake will eventually cool and solidify. So just want to restate that from USGS. I've been saying the same thing, but I think it helps to hear it from them as well. Question from Jim Pushow to the USGS volcanoes. You think it's possible for the current drop-down crater to fill to overflowing? We've talked about that on this broadcast as well. USGS Volcanoes replies, that would take quite a while. It seems unlikely that it will last that long based on historical patterns of eruptions. We've talked about that as well. But it is possible. A few month-long eruption occurred at the summit in 67 to 68. And of course, there was steady activity for a century in the 1800s. I mentioned that as well. We're going to cover that tomorrow. Effusion rates usually wane with time, though. I also talked about that. So after the initial pulse, things would probably continue to slow in this eruption. Continue to slow. So they're seeing it slow already, right? That's what we're seeing there. All right, another question. Similar kind of question from Mark Ord. Does this suggest eruption is likely to end soon? They reply, not necessarily. The fact that the summit is deflating means that more magma is leaving the storage than was entering. And so at some point, it'll fall below a pressure threshold needed to sustain an eruption. But we don't know how long it'll be before that happens. Traditionally, eruptions like this have lasted hours to days. The last eruption was 1982, and a lot has changed since then. All right, so there's another follow-up below on this thread to John C. Weaver. The deflation is due to magma leaving the subsurface storage area and reaching the surface, leaving the chamber to erupt. The seismicities are definitely associated with the magma movement, but most of with magma getting from the chamber to the eruptive vents now, and even that has diminished because a pathway has been established. So there isn't as much rock breaking now as there was initially. January won't necessarily be hot. What that means is this eruption may not last until January. Okay, that's what they're saying. Before 1983, this was largely how Kilauea operated, an eruption or intrusion every few months to years, with occasional strong earthquakes interrupting things, and occasional longer-term eruptions like Mauna-Ulu and a summit. But the chamber would pressurize, the wall would break, magma would squirt to the surface, causing eruption and bleeding off the pressure until the eruption stopped. And then the pressure would build back up again as more magma was supplied from beneath until the chamber cracked once more. A cyclic process. It may be that we're becoming more to that sort of pattern now. So they expect this to be short-lived, but for it to happen again. Right? So, all right. Let me come back over here. Our summit cameras. I'm going to leave this here on the screen for you guys while I try to look up some questions, and then I'll bring up any more graphics that I may need. So, all right. Thanks you guys for tuning in. Hello, and thanks for bearing with me until I got to all your questions. So, all right. Questions here. Shout out to you guys. I see people watching from Vietnam, Indiana. Thank you guys for tuning in. Yeah, so someone is asking, or commenting, as the lake keeps filling up, the pressures, as you're talking about now, may increase earthquakes and, as you said, open new fissures. So that could be. It all depends on the actual rate coming out, right? If the rate coming out is actually slowing, it's doing that in response to essentially that pressure bleeding off. So that's why we expect this eruption to kind of be relatively short-lived compared to years long as eruptions we've had more recently at the summit of Kilauea. And let's see here. The follow-up being, it seems lateral vertical pressure may open back up the east rift and head back down established tubes towards Puna and Leilani. Right. So the East Rift Zone, certainly Upper East Rift Zone has been quaking, has been inflating and uplifting even in the last few months. And so an eruption on Upper East Rift Zone in Mauna-Ulu is already a possibility. You know, there's pathways there already. We haven't seen as convincing signs of that pressure reaching past there. Now, at some point that is going to happen, because it's a volcano, and the rift zones are the way that the volcano moves its pressure from the summit down to its flanks. So it's going to happen at some point. That can happen more passively or more actively, right? There have been times in the past where that's happened, and eruptions have happened around Makapui, or around Napau, or around Pu'o'o. That's a much more likely area for that kind of pressure to be relieved. Now, depending on how the south flank is moving, how much it opens, and how everything is set up within that pathway, which is between a half-mile deep and about a mile and a half deep, 1 to 3 kilometers down, then it can move all the way out, possibly all the way out to the ocean, as we believe happened in 1924, with another major event that we think will take more priming than we have had so far. But in the next few years and decades, that's what we expect is going to happen. It is going to be more pressure to push its way around into that rift zone and through those other weaknesses over there. What we're seeing now, though, is that the cap above the magma chamber, all that rubble, the combination of all that cracked ground and all the pulverized rock that's filling it, that is weaker than the pathway around the rest of the rift zone. So as long as we have a bunch of rubble that we can kind of come up and through, and we haven't filled this crater that much, then it's more likely to come out at the summit. And once the summit gets filled in and we actually reform it to actually fill in that whole collapsed pit, then it gets more and more likely that we can actually put pressure down a rift zone towards the Upper East Rift first, and then the Middle East Rift around Pu'u'u, and then possibly further down. But actually the Lower East Rift is a place that erupts the least often of this sequence, right? Because it's got to go it's got to pressurize the farthest away from the summit. So I know there's a lot of concern from people, and there's a lot of trauma from 2018. People who are really worried about this activity leading to renewed activity in the Lower East Rift Zone. We can't say there's a zero chance. There's always a chance it's a volcano, it's a rift zone. But right now, it seems that the signs that we're seeing, and this could change, the signs that we're seeing are that there's much weaker ground at the summit, and the lava is going to come out there first. And that's also the pattern we see over the last decades and a couple of centuries of eruption on Kilauea. So, and that will be more evident when we go through that details of collapses we're feeling tomorrow. I didn't want to add it on today because I've already been going an hour and a half, and it's a whole lot. It's a whole other story and a whole other can of worms to get into. I am in Hawaii for those guys who are asking. Shout out to Australia. See you guys watching from Australia. So someone is saying, it's a start 98 once again, with only 10% lava released in 2018 from the main chamber. We could see it fill 1K to 1.5K feet head down that East Rift Zone. It's possible. It's possible, and I certainly think the Upper East Rift Zone is certainly in play at any point, right? And that's the area between Kīlauea Iki to Mauna Ulu, right, along the Chain of Craters Road. All right. All right. Do I forecast another large earthquake? I do not at this point, and the reason being, I won't go into it now, but we have seen GPS signals on Kilauea's south flank. The south flank is actually moving. An earthquake is a relief of build-up pressure from something not being able to move. And so the fact that it's actually so mobile and moving in the aftermath of the 6.9 earthquake on May 4th, 2018, that south flank is still moving along. And so because of that, I don't think we have another big earthquake coming. On magnitude 6 kind of style. Now, of course, these magnitude 3s and 4s, that's possible because that's kind of a smaller local adjustment within a summit of the volcano. All right. All right. Someone is saying, do we know what the volume of lava has come out for the last 30 or so years? I'll have to add that up for you, Randy. So I'm not sure the total over the last 30 years. I could try to kind of add it all up here, but pool era average of 4 meters cubed per second for what was in the end 40 years, for 35 years. And then plus everything 2018 as well. All right, shout out to Norway. Thank you guys for watching. Let's see. Question: how solid is the floor beneath the lava lake? Is it the strength of the floor itself upholding the growing lava lake? Well, so it is the strength of the floor, but it's all that rubble that's in there. It's rubble and rocks, and that stuff is the same. Even if it's not as coherent as the lava, it's the same density more or less. It might even be more dense because lava is very vesicular. It's got a lot of bubbles trapped within the lava. So once it all gets powdered, you actually can have less void space, and so it might be more solid down in there, but not strong, right? Not strong to getting pushed aside when magma's pushing at it. Now, gravity, there's actually a whole bunch of stuff below that, so there's nowhere for it to go further in, but it certainly can pop up through that rubble other places as well, right? It can come up on the other side of the crater through the rubble as well. It's certainly possible at any point in time. Possibly the next eruption might do that. We'll have to wait and see. All right. Let me see if I can scroll down here. The ETA for how long it's going to come up, that's going to be something we have to calculate. I'll have to actually make a little model with the shape of the pit, and how it actually changes, how the elevation kind of slows as it rises with the constant volume and all of that. So we'll leave that for a future day as well. All right. All right. So I think I have covered one set of questions, and so I'm coming to you guys on Facebook. And thank you guys for joining on Facebook. Let me see here if I can get to see the set of questions, and so I'm coming to you guys on Facebook. And all right. So from the beginning, what's the worst case scenario? Could she clear her throat and clear all the debris out? The worst case scenario is always that there's more magma down underground that comes up faster than anything else that's come up so far. That seems to be very rare. It did seem like it happened in 1790, and there was some question about 1924, not as likely 1924. So maybe in 1790, possibly in the years before that, the centuries before that, when a volcano was going through a more explosive phase, it might have done that more often. We're not in an explosive phase now. We had a question of whether we might switch into an explosive phase. That doesn't seem to be happening, at least so far, right? We seem to be skipping ahead to the refilling stage, and we're refilling so much more in one eruption now than the post-24 sequence that I've been referring to actually did, right? So we have a huge amount of lava coming out. It's filling in that spot, that area, right? By the way, 10 million cubic meters is a lot of lava, right? It's that over 20,000 Olympic swimming pools. But if you compare to what came out of Fissure 8, we're talking about, or not even what came out of Fissure 8. Let's talk about the size of the crater, the actual pit at the summit. The pit at the summit is 0.8 cubic kilometers large, right? Estimates of the lava coming out of Fissure 8 are actually higher than that, up to 1.2 cubic kilometers, right? So if we take the 0.8 of the summit that's collapsed, how much has this volume of lava refilled it? If we take 10,000 cubic meters, the answer is about 1.25 to 1.5%. 1.5% is how far we filled the collapse pit of the 2018 eruption with this new eruption. Even with a super astonishing rate of rise of the lava lake we see in the video, almost reaching the vent level right over here. Keep an eye on this thing. This lake level is rising almost to the vent right over there. So that's really it. It does seem okay now. We got our biggest concern was that when this eruption began, it might come up at a faster rate through the pond of water that was already there, and that might cause explosions. Since that did not happen, it came up slowly enough to actually vaporize the water instead of actually explode it away. I don't anticipate any change in the dynamics that way, right? I don't see any reason to change to expect a change in what's happening just on that. We have to see new signals, new inflation, new tilt response, new earthquakes, those kind of signals to say, oh, there's more magma coming, and it's coming from a certain area, it might be coming faster, and that would be our worst case scenario, but that we don't see any sign of that happening at all. All right. So next questions. All right, so Vancouver, Washington. Shout out to you guys in Vancouver. What about residents and homes in danger? So the best thing about this eruption is it's all within a national park. In a national park, there is no one that lives in the national park. Everyone that's in the park is there by choice, right? And part of the reason National Park has been expanding its holdings over the time, sometimes forcefully, and that's a whole other story, but is because these are areas that do get covered with lava. And that area is great to have it be National Park because it's not going to burn anyone's house down. That's why there have been discussions, and it's harder in Leilani, right, of like how could you turn that into a park to kind of preserve it also for tourism, but also to prevent future damages and losses, because if it happened there once, it's going to happen there again. It's just a matter of how long it's going to be. And we've talked in 2018, like, you can get 60 years of paradise in between eruptions in some of these areas, but it's going to come back at some point one day. It's the nature of living on a volcano. So there are no residents in danger. There are no homes in danger. There are no structures in danger. The danger comes from the gas. So if people are asthmatic and live downwind, that could be dangerous. If they're growing crops downwind and now they have all these glass particles and shards falling on their crops, that can be dangerous. If you have cattle and the cattle are having to breathe this, that could be dangerous, right? That's the impact as more to agriculture and to air quality, right? And you see Kona side, the sunsets have changed. People in Kona having to deal with filtration. In 2018, people actually had to move from Kona because the air was so bad you couldn't be outside a lot of the time, right? So we're nowhere near that level yet, but we are seeing bad air quality in Kona once again, and that's sad for people who enjoy the sunsets in Kona, because they've had 2 years now of clear, beautiful sunsets, bright, vibrant colors they hadn't seen since the 1980s before the pool eruption. So, all right. More questions. All right, I see that Kristen Wolfgang, thanks for answering the question about the danger. Someone else is, thank you guys for enjoying the presentation here. Obviously, it's a very kind of, I have my unique take on things here. And someone's reporting coming down the saddle road, you couldn't see the ocean. So yeah, that's how much fog there is as well. You can see the glow in the clouds. So yeah, there's a lot more lava surface. That means it can reflect on the clouds a lot more brightly as well. So all right, guys, I'll keep going through the Facebook questions, and I'll wrap it up here after that. So are the raindrops near National Park becoming acid rain? The plume is blowing downwind to the southwest, and then in that areas you can have acid rain if you do have an interaction with water, yes. It is bad for vehicle body metals, corrugated roofs, catchment tanks, yes, absolutely. Living in fog is a whole other topic, but yeah, many things don't last between the fog and then the fact that we're on an island, we have a lot of salt air corrosion as well. Air is salty everywhere. There's quite a lot of corrosion in Hawaii on metals, yeah. All right. So